You ever just look up at the stars and feel safe? Like they're so far away, nothing up there could ever touch us down here? Yeah. About that, December 27th, 2004. Scientists across the globe were sitting at their instruments when suddenly, every satellite went haywire. Radio telescopes screamed. The Earth's magnetic field rippled like someone had just thrown a stone into a pond. And for a fraction of a second, our atmosphere lit up with more energy than the sun hits us with in an entire day. Something from deep space had just punched our planet. Not with debris, not with light we could see, with raw, invisible power that traveled 50,000 light-years and still hit us hard enough to shake the entire ionosphere. Hard enough that if you'd been looking at the right instruments, you would have sworn something just went terribly, catastrophically wrong. That something was a star, or what used to be one. Let me take you back for a second, because this story doesn't start in 2004. It starts 50,000 years ago, back when humans were still figuring out how to make fire properly, when we painted on cave walls and had no idea what those little lights in the sky even were. 50,000 light-years away, in the constellation Sagittarius, there was a neutron star. Now, if you don't know what that is, imagine taking something with more mass than our sun and crushing it down until it's only about 12 miles across. The entire thing, 1 million Earths worth of matter, compressed into something the size of a city. The atoms themselves are crushed so tight that a single teaspoon of this material would weigh about 1 billion tons. These things are already terrifying on their own. They spin. Some of them spin hundreds of times per second, shooting beams of radiation out into space like the universe's most dangerous lighthouse. We call those pulsars. But this one was different. This one was a magnetar. Take everything scary about a neutron star and multiply it. Magnetars have magnetic fields so intense they break physics as we normally understand it. We're talking about a magnetic field 1,000 trillion times stronger than Earth's. Strong enough that if a magnetar passed within 1,000 miles of you, it would pull the iron right out of your blood. The atoms in your body would stretch into thin shapes. You'd be gone before you even knew what hit you. But they're far away, right? They can't hurt us. SGR 1806-20. That's the name we gave this one after we found it. It had been sleeping out there in the dark, this tiny spinning ball of crushed matter and impossible magnetism, just doing its thing for who knows how long, until something went wrong. Picture the surface of this star. It's not like the sun, all fluid and flowing. It's solid. A crust of iron nuclei packed so tight it makes diamond look like cotton candy. But underneath, there's this ocean of superfluid neutrons, and the magnetic field lines are tangled through all of it like the worst knot you've ever seen. Stress builds. The star's own magnetic field is fighting against itself. The crust is straining. And then, like a rubber band pulled too tight, something snaps. The crust fractures. Just a little shift, maybe less than 1 millimeter, which doesn't sound like much until you remember how much mass we're talking about. That tiny shift releases more energy in 1/10 of a second than our sun will produce in 100,000 years. The surface of the star explodes. Not the whole star, just the surface, but that's enough. More than enough. A starquake. That's what we call it. But that word feels too small for what actually happens. A wall of gamma rays erupts into space. The most energetic form of light in the universe, the kind that goes through just about anything, moving at the speed of light in every direction. And one of those directions, by pure chance, pure cosmic lottery, is aimed at a small blue planet orbiting an average yellow star in a quiet corner of the galaxy. 50,000 years pass. The light keeps moving. It crosses distances so vast that if you tried to drive them at highway speed, you'd need trillions of years. Passes through clouds of dust and gas. It passes dead stars and newborn stars and planets that never knew life. And then it gets here. December 27th, 2004, 21:30 and 26 seconds Universal Time Coordinated. The wave hits. The gamma rays slam into Earth's atmosphere and immediately start ripping electrons off atoms. The ionosphere, that layer of charged particles way up above our heads that helps bounce radio signals around the planet, suddenly has 10 times more electrons than normal. GPS satellites stutter. Radio communications across the entire daylight side of the planet go fuzzy or cut out completely. The Swift satellite, designed to detect gamma-ray bursts from distant exploding stars, was nearly blinded. Its detectors maxed out immediately. RESI, a solar observatory, went into emergency shutdown mode to protect itself. The International Gamma-Ray Astrophysics Laboratory caught the burst, and for a moment, scientists thought their equipment was broken because the numbers didn't make sense. Because here's the thing, gamma-ray bursts happen all the time. We see them from galaxies billions of light-years away. Massive stars dying in supernovas, black holes being born, the universe's most violent events. But they're far away, safe, distant fireworks. This was close. Cosmically speaking, this was right next door. And it was aimed at us. The initial burst lasted 0.2 of a second. In that fraction of a heartbeat, more energy reached Earth than we receive from any source besides the sun. Then came the pulsing afterglow, waves of radiation that kept hitting us for 6 minutes, each pulse weaker than the last but still incredibly powerful. If you were an astronomer that night, you were freaking out. If you were anyone else, you had no idea anything had happened. No pretty lights in the sky, no sound, nothing you could feel or see. Just invisible death screaming down from the stars and washing over our entire planet. Scientists pulled the data. They did the calculations. And then they did them again because the numbers were insane. The blast released about 10 to the 46 joules of energy. To put that in perspective, that's more energy than the sun produces in 200,000 years. Released in less than a second. Some estimates put it even higher. And then someone asked the question nobody wanted to ask. What if it had been closer? We started doing the math. SGR 1806 to 20 is 50,000 light-years away. That's pretty far. The radiation spreads out as it travels, following the inverse square law. Twice the distance means a quarter of the intensity. But flip that around and it gets terrifying fast. At 10,000 light-years, 25 times closer, that burst would have been 625 times more intense. Our ozone layer would have been damaged. Not destroyed, but hurt. UV radiation from the sun would have increased. Ecosystems would have felt it. At 1,000 light-years, we're looking at total ozone destruction. The protective layer that keeps the sun's radiation from sterilizing the surface would be gone. Mass extinctions. Genetic damage to anything that couldn't hide deep underwater or underground. At 10 light-years, the distance to some of our nearest neighboring stars, everything on the surface dies. Period. The gamma rays would hit the atmosphere with so much energy that they'd create a cascade of chemical reactions. Nitrogen and oxygen would bond into nitrogen oxides, choking the sky with brown toxic clouds. The ozone would be completely annihilated. And then the radiation would come down. Unfiltered. Any life would have to be miles underground or deep in the oceans, and even then, the collapse of the food chain would probably finish off anything that survived the initial blast. And here's what keeps me up at night. We know of about 12 magnetars in our galaxy. We've probably only found a fraction of them. They're small, they're dim, and space is really, really big. There could be dozens more we haven't spotted yet. Most of them are far away, but not all of them. There's one about 9,000 light-years away, another at 13,000. Most of the ones we know about are distant enough that even their worst tantrums wouldn't do more than mess with our satellites and radio. Probably. But we don't know where all of them are. Worse, we don't really know what triggers these starquakes. We have theories. Magnetic field stress, crustal settling, stuff like that. But we can't predict them. A magnetar could be sitting out there, perfectly quiet for millions of years, and then tomorrow, snap. No warning. Just a wall of gamma rays moving at light speed toward anything unlucky enough to be in the way. And if one went off close enough, there would be nothing we could do. No time to prepare, because by the time we saw it happening, the radiation would already be here. Light speed doesn't leave room for emergency meetings. The 2004 burst gave us a glimpse. It showed us that space isn't just empty nothing between us and the stars. It's full of things that can reach across the void and touch us. The universe is not a museum we observe safely from behind glass. We're in it, part of it, subject to it. Scientists estimate that a nearby magnetar burst could have contributed to at least one of Earth's mass extinctions. The Ordovician extinction about 440 million years ago, when something like 85% of all species died. The pattern fits. A long die-off, especially of things that couldn't hide from increased radiation. We can't prove it, but we can't rule it out either. And it could happen again. Right now, as you're reading this, there are magnetars out there, spinning, building stress in their impossibly strong magnetic fields. The universe doesn't care about us. It's not out to get us, but it's not protecting us either. We're just here, on this little blue world, hoping that when the next cosmic gun goes off, it's not pointed our way. The 2004 event changed how we think about space threats. We'd always worried about asteroids, comets, things we can see coming. But this was different. This was a star 50,000 light years away reaching out and slapping our planet hard enough that we felt it. It made scientists realize we need to be watching for more than just rocks. We need to know where every magnetar in our neighborhood is. We need to understand them better. Because the next one might not be 50,000 light years away. Some of the researchers who studied the 2004 burst wrote papers with titles that sound like science fiction. Could a nearby magnetar threaten Earth? The answer, by the way, is yes. Absolutely yes. We just got lucky that the nearest ones are far enough away. Probably. There's something deeply unsettling about the idea that a star you can't even see, that exploded when humans were still learning to make tools, could reach across the galaxy and kill you. It violates our sense of safety. We know about dangers on Earth. Earthquakes, volcanoes, storms. We even know about space rocks that might hit us. But invisible waves of energy from dying stars? That's a new kind of terror. And the thing is, it's not even that rare cosmically. Magnetar bursts happen. Not often, but they happen. We've detected smaller ones since 2004. They just weren't aimed at us, or they were from magnetars so far away that by the time the radiation got here, it was weak enough to barely register. But in a galaxy with hundreds of billions of stars, some of which are neutron stars, some of which are magnetars, the odds aren't exactly comforting when you think long-term. Over millions of years, over the lifetime of a species, the chances of getting hit by something nasty from space go way up. We got lucky with SGR 1806-20. It was far enough away. If it had been 10 times closer, we would have had a very bad day. 100 times closer, and we might not be here to talk about it. The scientists who tracked the 2004 burst said it was the brightest event they'd ever seen from beyond our solar system. Brighter than any supernova, any gamma-ray burst, anything. For that fraction of a second, that tiny spinning star 50,000 light-years away was the brightest object in the entire sky to instruments that could see gamma rays. And we never saw it coming. That's the other terrifying part. We can't predict this. We can watch magnetars, sure. We can see them pulsing, measure their magnetic fields, track their behavior. But we can't tell you when one will starquake any more than we can tell you exactly when the next earthquake will hit California. We know it will happen eventually. We just don't know when. So we watch. We build better satellites. We model what would happen if different scenarios played out. We hope that we're not sitting in the cosmic firing range. Since 2004, we've found more magnetars. We've studied them in more detail. Every observation gives us a little more information, a slightly better understanding of what makes them tick, what makes them explode. But we still can't predict it, and we still don't know where all of them are. Somewhere out there, right now, there might be a magnetar building toward its breaking point. Its crust might be stressing, cracking at the atomic level, ready to slip and unleash hell. It might happen tomorrow. It might happen in 1,000,000 years. It might be aimed at empty space, or it might be aimed right at us. We wouldn't know until it was already here. Sleep tight. So here's my question for you, and I really want to know what you think. If we detected a magnetar close enough to be a real threat, say within 1,000 light years, and we knew it was unstable, what would you want humanity to do? Do we tell everyone and risk panic? Or keep it quiet and hope for the best?